Okay, well, we've heard some really nice scientific studies this morning. I've learned an enormous amount from all of you, and thank you for your talks. Uh, I'm gonna, I'm going to the other side of the spectrum here. I'm going to be talking about engineering and concrete rather than these extremely sophisticated liquid crystals and bio nanoparticles and enhanced solar absorbing materials. So let's go straight to first what the problem is that we're trying to solve. But before that, in case you haven't been to the United States, New Jersey is a little peanut-shaped state where the star is in the center picture. That's where I am right now. Uh, and if you go in this building where my arrow is right now and go to the end of the building, you will find my office. And my Rutgers is one of the few places in the United States where you can actually go fly in an airplane and then get in a train and actually be where you need to be. Uh, so uh, you're all welcome to come by if you ever find yourself in the United States. Uh, okay. And this is my group. Um, I am one of the luckiest guys in the world to have such vibrant and hardworking students. Um, they work hard and they play hard, and I wouldn't be giving this talk if they didn't all make massive contributions to the work. So um, as you've heard from our distinguished president of the United States, he thinks climate change is a hoax. So I want to first just talk about that for a moment. Um, this distribution of temperature and CO2 concentration has been experimentally documented. These are not people doing magic. They're taking these huge cylindrical sections out of the Arctic area, and they're measuring the gas compositions and isotopes so they can actually determine what the temperature was like. And as far as I know, they're almost back to 4,000 years ago. And what you see is that the temperature has followed a similar trend to the CO2 concentration until we get to the last 100 years, where the CO2 concentration has gone way beyond uh, anything that's been seen before in history. Um, this is what I know from experimental data. I've seen people come to me and say, no, the CO2 concentration has gone way up millions of years ago. And all I can say is, where is the experimental proof? All we know is for the last few 100,000 years, um, it's been very predictable, the cyclings of temperature and CO2 content, and it isn't now. Uh, the other thing is we do know that we emit about 36 gigatons of CO2 a year. I think we're getting closer and closer to 40. And uh, we're emitting about 1/3 of the amount of CO2 that nature emits. So the one question you have to ask yourself is if you have any kind of equilibrium process where you're changing, uh, the amount of gas that's being emitted by 30%, you have to believe that some sort of change is going to take place. Whether you believe the climate forecasts or not, it really doesn't matter. The point is that we're producing an abnormal amount of this gas for the first time, at least that since we've been documenting the climate uh, of the world. So I believe climate change has something to do with this CO2 concentration. We can argue about that over a beer. Um, the next slide, I just want to bring up at least how I view what I do as a faculty member. Um, in about 2006, I committed all of my research to sustainability. Before that, I was working on biomedical materials, optical amplifiers, and piezoelectric materials, among other things. A lot of high-tech stuff. And I just dropped it all and started working in this area. And what sustainability really is it's got three different lenses to it. One is the societal impact, how it impacts on people's ability to grow food, and to be able to survive peacefully. As everybody has seen, uh, we've had way too many wars about oil. Imagine what's going to happen if the climate goes out of control. I mean, I think things will get worse in that regard. There's economic aspects to it where, for example, even in magnetic materials that are very important for electric power and electric power generation, automobiles, etc. Um, uh, Even the distribution of rare earth elements and their accessibility could lead to conflict. So there's economic aspects of it besides the fact that there's an environmental aspect. Since the early 1970s, the Chinese made a very strong commitment to the harvesting of rare earths from their own resources. Uh, we can't fault them for being smart. They knew this was going to be important and they had long-term planning to do it. The one thing they didn't do, though, is they did not take into account the environmental impact of processing rare earths, where there's some really seriously deadly organophosphates that they used uh, and continue to use for isolating these materials. So if we develop a process that has a huge impact on the environment, it has economic impact and has societal impact, that's what really creates a what I call sustainability, and what the Rico Corporation from Japan was the first to define in the 70s. Um, so these are my specific wishes for sustainability, that I don't want to use high energy processes. I want to introduce recycling wherever it's possible. And I want to introduce the concept of carbon negativity, meaning that carbon negativity is the ability to use more carbon than you generated in the process of manufacturing a product. Um, and in order to get anybody with money interested, we need a product that's going to cost less than what the incumbent technology offers, and it needs to perform better. And then if we want the world to adopt it, then we need to work with raw materials that everyone has, not specialized materials that can only be used in one part of the world, perhaps. Um, so one of the things that I'm thinking that's important from the societal aspect is a lot of times people equate environmental respect with higher prices and penalties on companies. Um, what I'm trying to do is create what I like to call greed-based initiatives, where people who only care about money will do it because they can make money. Uh, and I don't personally believe in that, but I believe to get people with money to cooperate, you have to uh, basically attract them like a mouse is attracted to cheese. Um, so that means you have to really get to a point where you have something that's practicable and profitable. So there's a lot of different climate tech problems you can choose from. Um, and My interest is in carbon capture and carbon utilization. And I'm interested in having concrete utilize CO2. And at the same time, I'm going to show you how I can use the cement and concrete industry to also create a network that supplies CO2. So I'm trying to solve these two problems at the same time. And what's interesting is when you look at the whole climate tech area, uh, it's a market that's growing really quickly. By 2000 and 2030, the market's going to be easily above $1 trillion, um, which is about the size of the concrete market currently. So why pick on cement? Well, a lot of people may not realize this, but in the manufacture of cement, uh, it generates the largest segment of industrial CO2 emissions, bigger than even steel manufacture, where when you make steel, you're adding iron ore and carbon, and you're burning up all that carbon so you can reduce the +2 and +3 states of iron-based minerals uh, to the metallic state. Um, but nope, cement emits more, and the main reason is because we use so much of it. Right now, we're generating about 4.3 billion tons of cement each year. And it's going to continue to grow as more and more civilizations use cement. Uh, Now, the manufacturer of cement uh, is a very large scale process. A typical cement mill will generate about 2,000 tons of cement a day. And it costs the cement mill approximately $1 million a day for their manufacturing process. So later on, I'm going to show you that I did a trial at a full-scale cement plant, um, and we'll tell you about some of the results we got there. But the key thing is that we actually were able to get to a point where we convinced the cement company to try making our product instead of their product, um, which meant that they had to they basically spent $1 million just to do that demonstration. So there are high temperature processes, which I'll get more into, and then there are what we call finish grinding processes. So you can imagine, this process is running about 1600 degrees C, or maybe as low as 1450. And you can imagine this process is basically a device that spins with these large rocks inside that are designed to crush the cement into a fine powder. And so if you look at the actual contributions to CO2, it's approximately 3.5 billion tons a year. Um, I would argue that it's right now it's probably close to about 4 billion tons a year because this data is like 2019 data. And the Chinese have really increased their production of cement by a large margin. Uh, we'll talk more about why limestone emits more the CO2 than the fuel used to heat it or running the mill itself. But first, I'm going to tell you about the technology that we've created. It's very unique because we said instead of making cement with a lot of calcium oxide, let's drop the amount of calcium oxide we're using by a factor of 3. And by doing that, you lower the energy because when you typically make Portland cement, which is the conventional method, you're adding approximately 2 calcium carbonates for every silica or 3 calcium carbonates for every silica. And the blend of tricalcium silicate and dicalcium silicate is what makes up what we call Portland cement. And a typical mixture, at least in the US, is typically made at 1450, but it could be as high as 1600. We just basically said, let's dial down the amount of limestone. Let's lower the temperature by 250 degrees. And by doing that, we're reducing the amount of heat that we have to put into the decomposed calcium carbonate because it's an endothermic process. And also, it's the most expensive ingredient. So we're also reducing the price of the cement. So what we managed to do with this just small changes is that we lowered the cost of cement by 40%. Now, it was interesting because when I first went to cement companies and talked about this idea, they thought I was out of my mind and that I would never make anything cheaper than what they're able to make. And in the first day I went to do this at a cement plant, uh, we already convinced them that they were wrong. Uh, and we were able to scale this process to 2,000 tons per day. We demonstrated a 34% reduction in energy on the first day, and we also demonstrated a 40% reduction in CO2 emissions. So if you think we're emitting 4 million tons of CO2 now, imagine me being able to take off nearly 2 gigatons of CO2 off per year from the cement uh, um, business. So the reason why the cement industry has never done this before is because usually when you take what's called calcium monosilicate, which is where my arrow is pointing, it does not react with water. And we all know that when you make concrete, you add water to harden it because what it does is it forms these calcium silicate hydrates that create a bonding structure that holds together the sand and gravel that makes up concrete. What we basically said is we want to make something that hardens with CO2 instead. And by doing that, our bonding agent is actually calcite or calcium carbonate and silica instead of these calcium silicate hydrates. So if you look at the math, at the end of the day, we estimated that we could reduce CO2 emissions at a cement plant by utilizing the CO2 and avoiding CO2 emissions by 70%. And we're also reducing the energy by about 30%. Um, and this is the tally here, but basically we're adding CO2 to the system. We're not making it carbon negative yet because we're still emitting more CO2 than we are taking into the structure. But on the other hand, it's a big improvement over what could be done if it were deployed on a worldwide scale. So I want to explain a little bit about how the CO2 works. Uh, these materials literally breathe in CO2 like we breathe in oxygen. So the idea is we put water in the pores of these cement particles. And what happens is the CO2 reduces the pH of the water so that the calcium is leached out of the particles and we form a network of carbonate. And we have the particles left over basically being calcium depleted calcium silicate. So they might have an unreacted core of material and they might have a coating of a silica rich rim. But other than that, it is actually a material that performs better than Portland cement. And I'll show you that in a moment. I think I'm going to skip this slide. This is just a pictorial representation of the process. We have to actually create open pores in the structure by removing enough water that we begin to get open pores. And we create this structure that has a silica-rich layer along with this massive network of calcium carbonate that holds everything together. And we went and we patented that structure because nobody had ever patented a structure like that that can create mechanical stability. So we call this process low temperature solidification or LTS. And there's a lot of advantages. First of all, we don't have to use small particles. We can use large particles. And in fact, we've even used minerals straight out of the ground that will actually bond together. Um, some parts of the world have a lot of monocalcium silicate, like Afghanistan, Mexico, and the United States. Um, we can process with water, and because it doesn't hydrate, the material doesn't solidify until the CO2 is introduced. The carbonation process is very rapid. From start to finish, we can make a product that's ready to use in about 6 hours. While with using Portland cement, you have to wait at least 3 days before you can even walk on it. Um, Portland cement shrinks. Our process doesn't show any shrinkage, so you can make really large objects and not see the typical cracks that you might see in a concrete structure, which gives rise to all kinds of new kinds of materials that you might be able to make this way, which I won't talk about today, but we've got some very interesting materials that have other uses. We can follow the carbonation process by measuring the weight gain from the CO2. We can also follow it with infrared spectroscopy. Um, and we do that. And so here's an example of some work that we've done where we're monitoring the carbonation of a solid in situ while curing the material. And the process is easy enough that I have my undergraduates make concrete in the lab and compare it to Portland cement. And then I have them break the two materials to compare their strengths. And my material is always stronger than the Portland cement material. But literally using a cake pan to make a tile, this steamer is used for potatoes and hot dogs in restaurants. And here we're taking a 12-inch tile out. Um, and they're beautiful looking materials on top of that because calcium carbonate gives materials a white appearance. And we're doing a lot of basic research now where we're processing some large and small materials by monitoring the atmosphere, the weight gain, the amount, the relative humidity, the amount of CO2. And we can create plots like this where we can measure the amount of CO2 going into the structure and then measuring the amount of water that's been taken off in order to open the pores. And even when we've looked at large objects, objects that weigh maybe about 20, 30 pounds, our reactor can measure the CO2 pretty close to what we measure when we use chemical methods for extracting the CO2 and measuring how much is actually in there. And usually, by the way, when we measure the amount of CO2, we usually do it 3 different ways. And they're usually within 1% of one another. But this is for the large reactor where we're cooking a lot of different materials at the same time. Here's a comparison of, I would say, the longest solidification process that we've ever done, because for a while we would just leave these things in overnight and check on them. And then we discovered that, hey, once we really learned how to do this well, we discovered that we can even solidify a material in as little as 40 minutes. And again, it's full strength. It doesn't gain strength later on like cement and concrete. So even in our lengthy process that I'm showing you here we're looking at time in days, and this is time in hours. So it's a much faster process. Also, look at the compressive strengths that we can get. We're getting close to 200 megapascals, and this was one of the very first trials we ever ran. While Portland cement, you're lucky if you can get up to 60 megapascals or 1/3 of the strength. So again, that's showing how we're improving performance I mentioned already we can make the cement at 2,000 tons a day, 40% cheaper. And here's an example of construction products that have been made this way. So this is a hollow core building slab that's used for parking decks in the United States. This is what we call a concrete masonry unit or a CMU. I call them cinder blocks. Maybe that's a New Jersey term. But we can make a slab like this. It's 30 feet long, 5 feet wide, and 8 inches thick. And it's ready to use in 6 hours. These are some of the performance properties of the material. This was the very first measurements we ever made on these materials. And the most important things that you see here is that we've gotten close to 10,000 PSI, which, is great for a concrete material. It puts us in the highest category of high performance concrete categories. And the shrinkage that you measure is literally an order of magnitude smaller than anything that you've seen with Portland cement concrete. And most important, there's this property called creep. And when you measure creep, what you do is you apply 1/3 of the fracturing stress on the concrete, and then you take it and you measure the material for a year and a half and see if it distorts in any way. And this measurement that we made is literally in microstrain. And it's literally in the noise or measurement uncertainty, meaning the material does not distort. While Portland cement easily shows creep that is orders of magnitude greater. So imagine how fast we can do construction if we started using material like this. So what's next? Well, I'm not really happy that we can make cement at an ordinary cement mill because, quite frankly, the cement industry doesn't really want to do this. They want to continue making the same cement that they've been making for the last almost 200 years. So they're trying everything but doing this. And during the questions session, I can answer the question of what they're actually trying to do to reduce CO2 emissions. But I thought, well, if they won't make the material out of cement plant, then I'm going to invent a process that's going to be simpler and cheaper than what they can do. So the goals for the work was to get a process temperature that's close to 4 times lower than what's being done in the industry, make the product as fast as they can, which it takes about an hour to make their product, and develop a process that can go to 2,000 tons per day. In the process of doing that, because we're decomposing carbonate, we still have CO2 being generated, but why not use that CO2 for hardening the material? And then we'll have a zero emissions process. So that's what we set out to do. And just to give you a perspective on how cement is made, here's a chart that describes it. First, most cement mills are located near limestone quarries. And then they grind the materials to a fine size. And then they will calcine the calcium carbonate separately or all together, but in this case, it's separate at about 900 degrees. And then they'll do a reaction with the calcium oxide and the silica to make the cement product. And I showed you a picture of a cement mill. They're big. And then it has to be ground. And the reason why it has to be ground is because you make this product called clinker. So these structures are about 2 to 3 inches in diameter, and they have to be ground in order to turn it into a powder. So that takes electricity as well. So one of the things we instantly saw is that if we can do a low temperature process, we can even avoid the formation of clinker. So you think about this multi-step process. Imagine if we can do all of this with one single step. And the answer is we can. So what we discovered is that if we make a mixture of calcium carbonate and silica, and we expose it to water vapor under pressure, we discovered we can make cement directly from our reaction vessel. And the key to doing that is getting the water partial pressure low enough that that we can be in this region here for calcium oxide, or in this region for magnesium oxide. So in other words, what we're doing is we're throwing literally a few drops of water into the reactor. And once the water completely evaporates, we're now in the gas phase. And we're going off into this region where instead of making calcium hydroxide, we're making calcium oxide. So that's our operating range that we can work within. And we're way below any kind of condition that turns water supercritical. So we call that unsaturated, which is basically another way of saying we have very low relative humidity. If you're actually working where water coexists, like when it's raining out, you're along this curve. And the calcium silicates will not form if you're on this curve. Instead, you'll form hydroxides. And hydroxides make terrible cement. So in our discovery process, we literally did thermodynamic calculations to figure out exactly what vapor pressure we needed to be at in order to form calcium monosilicate. And what we discovered is that we can pretty much operate at any temperature above 300 degrees C. And so this is what's called an X-ray diffraction pattern. It basically shows you that the only crystalline phase we form is calcium silicate. And this is what it looks like. And you can see it's a submicron powder, more of a platelet-like structure. But this is made directly out of the reactor. No high temperature process is required. And we believe the mechanism by which this forms is that water absorbs onto the surface of the particles, and adsorption layers have a liquid-like behavior to them, which causes solubilization to transport some, most likely a calcium species, over to the silica solid, and then grow the calcium silicate in the other layer that exists there. And we don't have any proof for that. We're hoping we get some research funding so we can prove that we understand the mechanism. We found that we can make a lot of other ceramic phases this way as well. We've made close to 40 different materials this way now. So the advantage of low temperature, for some folks, probably a lot of them, 50 atmospheres is a lot of pressure. We're looking at reducing this pressure and creating strategies for doing that. We use very, very small amounts of water, so we don't have to evaporate a lot of water. We're using raw materials straight out of the ground. It makes the phase that we want directly. We don't have to calcine it. We don't have to grind it. And because the temperature is below 400 degrees, we can use renewable energy like phase change salts to power the process instead of using fossil fuels. And the last point is we've figured that this also creates what we call a recyclable material. So let me explain that. When we're carbonating, we're adding CO2 to the system to make a mixture of calcium carbonate and silica. Now that's just the starting material for making any cement you want. So it's effectively a decarbonation process as well. And so we can use the carbonation process to capture carbon, store it, and transport it instead of using compressed gases and liquids. And I can use the cement synthesis process as a way of dispensing the CO2. So instead of using a compressor to get to a certain pressure of CO2, we can use temperature instead. So we needed to basically find the conditions that allow us to go this way and that way, which is basically taking the reaction in the forward and the reverse direction. Now, this was one of the first results we got, which basically showed that after we have calcium carbonated silica, we turn it into calcium silicate, we add CO2, we make cement again, add CO2, and this is one that shows that we could go through basically 5 cycles and pretty much emit and give somewhere in the order of about 60% of the CO2 when cycling it. Likely we'll be able to do much better than this. And if we're able to do much better, these are the storage densities that are possible with different calcium silicates. So if we look at liquid CO2, it's about 1.2 grams of CO2 per cc of storage medium, while calcium silicate is about 1.1. So we're as good as liquid CO2. Now, if we went to certain other materials like magnesium oxide, we could be 4 times better than even dry ice, which is pretty amazing. The other thing is that to capture CO2, it's thermodynamically preferred. It releases a lot of heat in the process. So when you carbonate something, even if you do it at room temperature, it'll heat up to about 40 degrees C. So there's a lot of energy that's stored. And these materials are very sensitive to CO2. So you can pick up CO2 directly from the air or directly from water, as well as flue gas. And you're probably asking yourself, well, if we make the cement a couple of times, is it going to be strong? What we found is that the material gets stronger and stronger the more times you recycle it. So you can see we're already over 200 megapascals, and that's more than 3 times the strength of Portland cement. So what's the future? The future, as I see it, is why don't we use cement to capture, store, transport, and dispense CO2? That way we can avoid having to build a $400 million CO2 processing plant. A CO2 business is also a cement business, and a cement business can also be a CO2 business. So because our process is so simple, I would like to get this process in the hands of a lot of small business owners, because people can do either kind of business by just setting up my process and doing it. On top of that, we can use waste concrete. We don't have to necessarily use calcium carbonated silica. So the supply chains for this raw material is going to enable us to actually fill the huge amount of material that's used for making concrete. And that's one of the most important things, because one of the things the cement industries can do really well is make lots of cement. But the other thing that could be done is we could have a lot more people making smaller amounts of cement and doing it everywhere, especially if they can get materials from demolition. And we've calculated the cost of doing that. And the cement is going to cost somewhere on the order of 1/5 the price of Portland cement. So right now, Portland cement's going for $150 a ton. Imagine us being able to sell it for $30 a ton. And the markets for cement and CO2 are large. If it's a simple enough process that anyone can do it, then we can create a distributed economy and make cement the largest sink of CO2 rather than being the largest emitter. So I'd like to acknowledge all the organizations that have supported our research, as well as the startup companies that have spun out of Rutgers University. And we have more spin outs coming out as well. Thank you very much.